Welcome to the Australian Water School, the home of demand-driven, industry-designed training for the global water sector.
Welcome to another great webinar brought to you by the Australian Water School. And our aim is to bring you highly regarded water scientists who communicate complexity with ease. Today, it's no different. Three really highly respected water scientists are going to speak about hydraulic model calibration to historical events. Chris, Bill and Phil. I'm the chair today, Trevor Pillar, and we're delighted to see so many joining us. Just have a look at that screen. Yes, it's across 78 countries, and that fills us with a great deal of joy and gladness that we're communicating and working with you in water. Thank you for joining us. It's fantastic. Three lovely colleagues, Chris Huxley, Bill Simon, Phil Ryan. Come on screen. Good to see you guys. Chris is a principal engineer for BMT, who developed TUFLOW with over 15 years experience in the field of flood stormwater modelling and floodplain management. Chris is a senior member of the hydraulic modelling software development team, also an adjunct lecturer at Central Queensland University, where he teaches hydraulic modelling. You'll pick that up. Very, very good to see you, Chris.
Thanks, Trevor.
Great trainer. Bill Simon works in TUFLOW as well, has over 30 years experience in flood hydraulics field. TUFLOW software was developed by Bill starting in 1989. So Bill is the author. Bill is a software business lead managing TUFLOW products and associated services. Great to have you, Bill. Wonderful. And Phil Ryan, also with TUFLOW, has over 15 years experience working on numerical hydraulic modelling tasks. Phil is currently software development lead for TUFLOW Classic/HPC hydraulic modelling software. So here we are, guys, the A team. Wonderful to see you. Phil, you're down in where? Northern New South Wales.
Yeah, Northern New South Wales in Bangalore, just inland from Byron Bay.
A wonderful spot to live, Byron Bay. That has the ring of hippie about it, but you're no hippie. this is the Aussie
Phil had to
speaking
shave
hip.
for this event.
I've let my hair get a bit long, actually.
I like it. You feel out of place, Bill?
Yeah.
No, this is the Australian theme coming out here. Everyone from all around the world. I know. I see Mexico, Iran, all over the place. Thanks for joining, everybody. We're just having a bit of an Aussie joke there. Right, we did a poll. Thank you, everyone, for answering those questions. That was wonderful. Do you want to have a look at that first up? Is that a good way to go?
Yeah, sure. Let's see. So what sector do you work in? Good mix there, government, consulting predominantly.
Yep.
I've specifically actually included content which will be useful for all. So even if you're from government, there's going to be lots of really good content here.
Must be good to have government understanding what consulting thinking and consulting understanding what
very
government
important.
thinking.
Yeah, absolutely. Yeah.
Okay, good mix, mostly over 5 years, but we've also got some people who've not done modelling before and through the earlier years. That's excellent. I've tailored content to that full range as well. So even if you haven't done much modelling, you should get something out of this. Here's an interesting question. What proportion of flood modelling you do uses models that are calibrated to historic events? So the biggest percentage there is 0 to 20%. And I was pretty much expecting that number. And because of this, I thought this topic was really important for us to cover, because I want to see us move from that 0 to 20, to a much higher percentage.
Well, there's certainly the numbers in this webinar to prove that there's a demand there. Thank you, everyone, for coming to join us.
Okay, when you build a new flood model and don't calibrate to it, or don't calibrate to a historic event, what are the most common reasons for not calibrating? It seems the majority was insufficient available historic data. Excellent.
What did you expect? That answer?
Was expecting that one. Yes, spot on. Probably those percentages as well, to be honest. So probably about the first quarter of the presentation will focus on collection of calibration data. And finally, let's see, what proportion of a flood study project budget is allocated to model calibration? There's a whole lot of different tasks with calibration being one of those. And there's actually a variety of answers going from did not have enough experience to answer that. That's completely fine. But if you did have the experience, it ranged pretty uniformly from 0 to 10 up to 20 to 30. Okay, that's a little bit surprising. We'll talk about that further during the presentation, I think. There's a slide that focuses exactly on that topic.
Yep.
About halfway through.
It's wonderful, everybody. Thanks so much for taking the time to answer those poll questions. It gives Chris, Bill, and Phil the clarity on who's on board today. And now, how we're going to do this is that Chris is going to kick off with 30, 40 minutes, 45 minutes of presentation. We're going to hand right over to Chris.
All right. Topic: hydraulic model calibration to historic events. Let's have a quick look at an overview of what I'll be talking about. First, we'll discuss why flood model calibration is important. I'll step through some data input considerations, different calibration data types, their accuracy, model input, quality control. Then we'll work through just a list of different model design considerations that you should take into account. So when you're translating your input data into a model, you're reading the data in correctly. I'll present 2 different case studies, which we'll use to demonstrate how modelling errors can influence results. And then we'll talk about model calibration reporting. There's actually quite a wide array of different ways that calibration results are reported, and also some statistics that are commonly used to assign a ranking or a calibration performance. Okay, first up, look, you might have seen the promotion for this on LinkedIn where I shared this video. Agencies commissioning projects and also the modelers building project models have a duty of care to the end users, and that's the community, that the models we develop are fit for purpose. And the responsibility for that, like I say there, lies in all parties. It's the governments, whether it be city, state or country, who are commissioning projects. It also relates to the actual consultants who are doing the work, if they are consultants doing the work. So we need to get the answer right, and the community expects that, and it's our responsibility to them. One of the challenges we face is that these flood models, these 2D flood models that we develop, are incredibly convincing. There's an animation there of a dam failure flume test where you've got water breaking out of a dam, pushing up against an obstruction. It looks great. Is it right? The only way that you can tell if these answers are right is to calibrate against known historic events. Otherwise, look, there's just no way to really know if the true bounds of uncertainty in the result from your modelling. I won't be talking about solution schemes too much. Bill actually covered that in a webinar, it's probably September or August last year. And you can find a link to that at the web link there. So at the TUFLOW website under our library and webinars, and just look for how wrong is your flood model. They'll talk through some of the features within the engine that influence solution accuracy, I guess. Calibration workflow. This here is a slide that just walks through the standard approach to calibration modelling. So from left to right here, first of all, the thing I do initially is confirm all of my input data sets are accurate. And I'm not just talking about your model data sets there, like your topography data and your boundary conditions, but also all of your calibration comparison data sets. It's your gauge data sets, your peak water level survey data sets. Once I've completed that task, I go about developing my first pass approximation of what I think would be a good model using all the available data. And once I've established that using all the industry standard values for Manning N and bend losses, when you've got 3-dimensional flow conditions that you need to accommodate for, I go about going through a calibration process, and that's what's displayed on the right. It's very important that you calibrate to lots of different events, not just a single historic event. Preferably, those different events should have a range of different magnitudes, small, medium, and large. And they should preferably correlate with lots of good available data. And recency is also important, because the model you develop should represent the current state of the catchment, so you need to take that into consideration. When I'm going through this process in a project, I typically actually start by trying to calibrate to a small historic event. In doing so, I'm focusing on the model's definition of the conveyance zones in the catchment, so your river channels in essence. Once I've calibrated that, I then test that and calibrate to a moderate size event, so we're seeing some overtopping of the banks out in the floodplain. Because if I've tuned in the geometry and the definition of the river, I know I can then just focus on the interchange between the river and the floodplain to get the levels right out in the floodplain. And then I do other larger events thereafter. And taking that approach, I feel like it's quite a systematic way to achieve a good calibration. It's worth noting, you won't get there first time around. There'll be lots of iterations. And I say this, and I've said this in lots of presentations, if there's any aspect of flood modeling where you learn the most, this is it. Nothing will test you more than calibration modeling, and you'll not come across any other situation where you can learn as much. I almost think of calibration modeling as dating. You know, this is the moment when you really get to learn the ins and outs of the catchment that you're that you're trying to model. So I think it was the first 6 months of dating. Prior to this presentation, Adam Berry, who's a local consultant here in Brisbane, actually posted a topic on LinkedIn calling out for more calibration. I agree with him wholeheartedly, and there was a really nice, frank discussion from lots of people in that chat. And there was one comment that I really liked, and this came from Terry Malone. Terry's very, very experienced and respected in our industry here in Australia. Spent a long time in the Bureau of Meteorology. He's also ex-Sunwater and SEQ Water. And what he wrote in that LinkedIn chat was, like in 2013, SEQ Water undertook a study of the Brisbane River, which calibrated to a suite of hydrologic models to 35 flood events dating from 1893. An objective method of determining model parameters was developed, which included data quality, rating reliability, event magnitude, peak ratio, volume ratio, goodness of fit. Extended beyond that, I've cut that out. I've adopted this approach to hundreds of models and thousands of events. So there's some nice information there that we'll circle back to when we're talking about our result presentation. But I think the key to everything he wrote there was this final sentence, which is it's easy to calibrate an event, but far more difficult to calibrate a model. What he's saying there is when you're calibrating a model, if you just do it to one event, yeah, you can fine tune that in quite easily. But if you're calibrating to lots of different conditions, that's where the real skill comes in as a hydrolake modeler. So it's more difficult. It can be done, there's no drama there, but it's just more challenging and you'll learn more doing it. This is where I just want to circle back to the initial survey question that we posed initially. What is a reasonable cost for model calibration relative to total project budget? And there was a good spread of results there, actually pretty much from 0 to 10% through to about 30-40% in the survey initially. This is the answer that I have, and what most of the people in that LinkedIn chat agreed to. They said it was around about 30% was a pretty good fit. It's worth noting that 30% relative to all of the potential, unexpected flood damage costs or costs associated with over-design of flooding infrastructure, whether it's levees, roads, bridges, is nothing. It is insignificant. So if anyone comes up and says, look, calibration is too expensive, you really need to think about all the flow-on costs of not calibrating, because they are far more. That's very much a call out to the people commissioning work. So that defines the need for why we calibrate models. Okay, we need it to get the right result. We need it because it means that as an outcome of that, our floodplain management of the greater catchment is done more efficiently from a dollar sense, I guess. Let's now think about modeling. And when we start calibrating, I like to approach this by considering systematically all the potential sources of error. Let's see, so there's data issues. That could well be issues with your recorded calibration data, your boundary condition inputs, your model geometry. How you translate that information into your computer simulation is also a potential source of error. So model input, data interpretation, also your model design. And also there's software assumptions and applicability. So hydrology modeling, hydraulic modeling. I'm going to focus on the two on the left. By doing so, I'm maintaining more or less a bit of an agnostic approach, because there are so many different software out there that if I start pointing out differences in different schemes, it would take up a lot more than 1 hour, I'll tell you that much. What I can say though is I've been through 5 of these AWS webinars to date where I've either been presenting or in the chat line behind the scenes. And each time that someone has asked the question, does TUFLOW produce the same result as HECRAS, because they both have a subgrid sampled topography approach? And the short answer to that is no, they don't. There are a huge number of assumptions that go into these different software. And to make an analogy of this, I'd probably describe it as, if you've got 2 cars, that subgrid sampling aspect of it is like saying, okay, 2 completely different cars with different tires, but they're using the same tread. So it's a very small element to what makes a software, or what creates the software that you're using. Let's now look at and start talking about calibration data accuracy. Off the back of Phil's presentation last month, there seemed to be a few people that didn't really understand the concept of the calibration data reliability. So we'll look at that in a second. Let's see, what sort of calibration data types are they? There's surveyed peak flood levels, maximum height gauges, watermarks on buildings or debris lines. You'll find continuous water level gauges, velocity gauging. Anecdotal evidence is also useful, and flood extent aerial imagery. What I will say to this, if we just focus on those surveyed peak flood levels initially, is I'm really calling out to all the counties, catchment authorities, cities. Whenever there's an event in your area, please go out there and collect data. And also, I'll just circle back to some personal experience here. It's really good if you can have interagency coordination during these events. Floods aren't limited to council boundaries or cities. Back in, when was it, 2008, I remember Phil and I were present for a pretty major flood event in Kyogle in the Richmond River County Council area. And I was really impressed at that time that the state government organisation, it's Office of Environment and Heritage now, they took a leading role there in coordinating the data collection exercise for that event for all the surrounding councils. And that sort of oversight and support from a high level is really useful. Look, there's lots of guideline documents that you can familiarise yourself with here when it comes to flood data collection. There's one there from Victoria. Another one that I'll look into a little bit more now is one from the USGS. And this one focuses entirely on the identifying and preserving of high watermark data. And I'm hoping this will answer some of the questions people asked last presentation about the data reliability. All right, when you're collecting this data, it's really important that you understand how reliable it is. Let's go into this a bit more. There's some debris lines on the right there. They look pretty reliable, I'd say. It's pretty certain that that's where the flood level got to. That may well be the case. In low velocity areas, it definitely isn't the case in high velocity areas. There's a quote from the report itself. You need to watch out for situations where high velocity flow is pushing debris up onto structures or onto trees. You can see there in the bridge, the velocity can push that debris up onto the structure itself, which can artificially make it seem like the water level is potentially higher than it was. Alternatively, sometimes you'll see trees which have debris around them. If they're small saplings, those trees may have actually collected the debris as they were bent over, and then after the event risen up, which also artificially makes the flood levels seem higher than they were. So you just need to be aware of these sorts of aspects. And I thought this video here presented it really nicely. It's nice to ground all of our work on real information. Look there, you can see behind the building and over in the background by the fence, that's a low velocity area, and the flood levels don't vary much there. Whereas in the high velocity zone, where you've got the loading up against the wall of the building, momentum is pushing that water up against the building, so it's elevated to start with, which is fine, but the variation in level there is pretty significant, just due to the turbulence. Next one, you might think, okay, a stain on a building is very reliable. It turns out you need to be careful about marking down your flood lines in a building as well. Some materials will actually seep they'll absorb the water and you'll get seepage, which will push that flood mark up. So just be aware of that. Another thing, when I was calibrating a model, this is back in the early 2000s, we didn't have much data because we had to backdate. We had to collect data well after the events. I think we were trying to calibrate back to an event from the 1980s, and the models just weren't coming anywhere close to this one mark that we thought had a high degree of certainty with it. It turned out that it was a high risk area, and that house had been raised about 2 meters, 2 years prior. So if you're collecting data from far in the past, look up your house raising records to just check that the level you're not referring to that was marked in pen on a wall is right or not. Mudlines, they look pretty reliable. The USGS just, I guess, puts out a warning here. Just be careful of receding soil, if saturating soil receding, because it can actually masquerade as a mudline from the flood, which would be inaccurate. At the end of the day, you'll get a whole range of different flood marks. This is an image from Phil's presentation again. And for the benefit of your own calibration, it's really nice to thematically map your reliability rating. So when you're tuning in your model, you know what sort of accuracy you should expect in those areas. At this point, once I've got all the data, I always do a regional continuity check. Just make sure it makes sense. Does the water go down as you move down the catchment? I also do a DM verification. So I just subtract the recorded level from the DM just to make sure there's not any major discrepancies there. If there is, that could be a survey error. Let's move on to gauges. Word of warning. Inland gauges will often use a local datum. They probably won't use your model datum. And if you're trying to calibrate to those without correcting for that offset, well, the model you produce is going to be completely wrong. Here's an example here where we have a 4 meter offset between the model datum and meters AHD, and you need to correct for that before you do your modeling. Similarly, down in coastal environments, more often than not, the datum relates to your lowest astronomical tide. And the reason for that is, in a nautical sense, the purpose of navigational charts and those gauges, the tide gauges, is to provide ship captains with an indication of how much water is available at the lowest tide, so they can judge where their boat draft will fit through the canals and channels. Now, if you don't correct for that, obviously you'll get the wrong answer as well. I think I've come across this last one in about 50% of the different studies that I've calibrated to, and that's where historically a gauge has either changed its location, so the agency has moved it, or alternatively the datum has shifted to correct for, I don't know, maybe shifting from imperial units to metric in Australia or for some other reason. So it's important to look back through that history whenever you're using this data, because if you don't, or you're checking against false data sets, I guess. Rating curves or velocity gauging. There was a webinar about this last week. I'll go into it ever so slightly from a flooding perspective. More often than not, you'll find that gaugings are done in non-flood conditions because it's a lot easier to get out in a boat and sample the data. What it means, though, is that in a lot of cases, the rating curve that is derived from velocity gaugings above those prior gaugings, up in the zone where we're interested in for flooding, is an extrapolation or a calculated value based on, cross-section Manning's calculations. It's important for you to know what approach the agency that created these ratings has used to extend the curve out to those higher flows. In many cases, I've found that the cross-section using the calculation is limited to the low flow gauging extent, not the whole floodplain, which relates to the flooded, wetted area. And if you make that mistake, well, the ratings that you're using will be completely wrong. So, look at the metadata, get an understanding of the range of uncertainty of these gauges, of these ratings. It's also worthwhile thinking about hysteresis effects and that influence on the uncertainty with single line ratings. They're pretty simple things, those single line ratings, and the range of uncertainty due to hysteresis can be quite significant. This here is from the Clarence Prince Street gauge. This is actually a really great example of velocity gauging throughout the whole event. Now I have to do this from the Grafton Bridge, which is over the river. It's a pretty rare data set, but very useful for model verification and calibration. All right, you've got all of your calibration data. You know it's accurate. If it wasn't using your model data, you've made corrections for that. You now are ready to start collecting your model input data sets. At the end of the day, a model will not correct for data errors. It's your responsibility to correct for those before you start using the data. So let's start looking at common data errors when it comes to calibration. For starters, this one might seem pretty obvious, but I've seen it done before. Use real recorded data. Don't use design event rainfall as an input for calibration. If someone said it was a 1% AEP event, don't just drop your 1% AEP event temporal pattern and rainfall depths in there and plot the results and say, oh, the model's calibrated. No, use real rainfall data. And you have to verify the recorded data quality before using it. There's a real example on the right there. There was, 9 different gauges in this catchment. Can you tell me which of those gauges went offline during the event? It's impossible to tell when you're looking at histograph like that. The one thing I like to do whenever I get these data sets is plot the tipping bucket data information in a cumulative sense. And from there, I basically just look for any data sets that trend horizontal before the time that I'd expect them to. In this graph here, you can see it's those 2 lower ones. It turned out that part of the catchment in this location, was where they received the most rainfall based on the daily total pluviographs. And if we hadn't have picked up that those 2 tipping bucket gauges went offline very early in the piece, we would have had no chance of calibrating that to that event. So something to be wary of. I mean, this should be pretty well known. Although LiDAR data appears very accurate, you still need to validate it. Because if there's inaccuracies in your topography data, those inaccuracies will pass through to your flood model. And I always do a check of my LiDAR data against known survey data sets. You know, most councils would have huge survey data sets and also information for all of the survey benchmarks throughout the region. So compare your LiDAR data against that just to confirm the accuracy. It's common for LiDAR not to have, or not to penetrate water. And that's what this image here on the right shows. It doesn't take a big stretch of the imagination to see that if you don't represent your waterways in your topography data set, you won't get the right result. On the left there, you can see a cross-section between the original data set and the amended data set that include the river bathymetry. This is a pretty nice looking DEM. You know, you can see some nice urban levees. You can actually even see the grain, like the crops growing in the field there and the rows associated with those. You know, what's your thoughts on the quality of this data? It looks pretty good. It's quite fine resolution. It's very recent. Let's just zoom into this area. Looks a little bit suspect, doesn't it? This is a perfect example of a very recent data set where it hasn't captured the in-bank bathymetry. And the tinning through there, which is basically from riverbank to riverbank, would cause no end of drama in your modeling if you tried to use that without supplementing in bathymetry data. In QGIS, I really like using hillshade symbology when I'm reviewing my DEM data sets. And that's how you get this sort of exaggerated presentation of the topographic changes. So something to look at if you're not familiar with that, hillshade symbology. Here's another example. Bridge openings are sometimes misrepresented in LiDAR. And I'll go through a couple of slides later on, which will show the actual impact of this, this bridge, or the lack thereof, on the modeling results. Bridges, they're pretty significant to the hydraulics. So as a quick check, I always go around and check that all the bridges have been cut out of the DEM if they should be or not. Another really useful thing to do when you're building a model is enforce your ridge hydraulic controls. This is the same data set as before with all of those rural levees. Computationally, the way that the solvers work is you get storage calculated in the cell, but then water breaking from one cell to the next is defined based on the topography along the cell face. If that face doesn't line up with those levees, you'll find water artificially breaking through them, which is what's shown on the right there. Once I'd enforce those hydraulic controls with break lines, I get the answer on the left, which is actually that's the right answer. Yeah, so always be careful with those hydraulic controls and enforce them with break lines. I'll just show you very quickly how we do this in TUFLOW. There's a really nice automated way to do it. I think Phil actually developed this in ASCII to ASCII. There's a link to the utility down the bottom there. Step one is to draw your break lines in manually. This data set looks pretty complex. It took me about 15 minutes. If someone's complaining they've got to draw something, pull them up. It's not that hard. With each of those lines, I just eyeballed it. I wasn't trying to get the exact crest. I was just trying to get close enough. I then set a sample distance, which is the DZ attribute, and the shape width, which becomes an inspection radius, and a process option, or shape option, which in this instance was set to max. And ASCII to ASCII will actually inspect a radius around every single 100-meter increment here and pull out the maximum value for inclusion in the TUFLOW model. So you've drawn that data set using the Z-shape template file, run ASCII to ASCII. It batch processes this really quickly. Here's the output. You can see that it's actually sampled at the radius that I've set, and it's pulled out that maximum value. Then it's literally just a matter of using that post-processed data set as an input directly into the TUFLOW model. So I go and add those, 6 different files, 2 different shape files into the model. The beauty of this is that you don't have to exactly pick up the crest when you're drawing the line. You don't have to be wasting time with that because that search radius fixes that issue for you. Next piece of advice, don't be lazy and just use online data sets without checking them. This is a NLCD data set, so it's a US data set on the left. There you can see it compared against the actual aerial imagery. It doesn't really reflect reality. I'm not sure how they created that data set, but it's very wrong in this instance. Without changing that to a manually defined data set, which I've shown there on the left, I couldn't have calibrated this model. Not accurately anyway. I could have calibrated it, but whether it would be right or not is a different story. Once again, mapping of land use, it doesn't take long. People complain about it, but that's just people being lazy. Once you've mapped the land use, it's very important that you use industry standard values. There's a link here that you should follow to a couple of different guideline documents. I think there's 3 in total. Probably the number one error I see people making is using non-industry standard values to tune in a model, when really they should be looking at other modeling aspects and correcting those. Yeah, so there's 3 different data sets in that guideline link. If you're working on an urban model, your pipe network data set is probably going to be pretty significant for the hydraulics. You need to go through and check that data set. And there's a lot of different ways you can do that in TUFLOW. We've got the pipe integrity tool, it checks for snapping, pipe direction, continuity, really easy automated way to correct for all those issues in your input data sets. Cell size is very important. If you haven't seen the cell size selection webinar from September last year, I recommend going back and looking at that. You want to choose a cell size where you know that if you made further adjustments, reducing the resolution, it wouldn't have a tangible impact on your result accuracy. Go back and look at that webinar if you haven't yet. That's a very important concept. And finally, go out to site, meet and talk to the locals. They'll have a lot of information that will help you with your calibration. That image on the left, that's from my hometown in Murwillumbah. The Byington Bridge, every flood gets loaded with debris. If you're not accounting for that in your calibration, you won't get the right result. That image on the right, that reminds me of a story Phil told me where in Newcastle, he and Bill were calibrating a model. I think it was the Pasha Bolker event back in, maybe it was 2007, 8, I can't remember. But anyway, when they were trying to calibrate, the levels all seemed off, and it turned out there was some shipping containers blocking some pretty major drains. So without accounting for that in their calibration, they could have changed some other things to get a result that really didn't reflect reality. All right, so we've spoken about data, we've spoken about model design. Let's now use a few different case study examples just to get a sense of how much results can change if you're not going through the systematic process of checking and building your models. This here is a data set from FMA Region 9 in the US. They issued a challenge back in 2019, I think it was, where it was a model data set. It was just one event. They provided the inflows. They provided the land use data. We actually didn't end up having to remap that ourselves because the national land cover database just wasn't of good quality. And they provide a 5 meter DEM. There were some issues in that, so we actually had to, like I said, correct for that bridge opening and also embed some ridge break lines just to get a good calibration. But I'll go into that in a second. They also provided 53 peak flood level marks, so we could test the performance of our simulation. This was the modelling process I took. Step 1, I just created a broad scale model at a really coarse resolution. And the purpose of that was to get an idea of what my inundation extents were. So that would then tell me where I should be spending most of my time fine tuning and looking at the data. If something's going to be dry, why would you go out and look at land use and whatnot out in those areas? So once I knew the general flood extent, I used industry standard values and definitions to set my land use and topography. I then did my cell size convergence testing, and it turned out the 30 meter resolution was appropriate. Then I did further iterations. There was 11 in total to fine tune the model. And then finally, once I'd done the 30 meter resolution, I actually dropped it back down to a fine resolution just to get a really nice looking result. The accuracy didn't change, but the results did look more resolved, I guess. Yeah. Let's look at this bridge. So remember this image from just previously, where the bridge was not represented in the DEM. The black numbers here are the recorded flood level, the red is the model result, and the blue is the difference between the two. Upstream of this bridge, you can see we're about 1.5 meters too high. Now, if we open up that bridge, surprise, surprise, we get a good calibration. Those levels are now really nicely in line with, or the model result is really nicely aligned with the recorded data. So focusing on these key areas, which will have a strong influence on the hydraulics, is really valuable in getting the correct answer. When it comes to checking my calibration accuracy, I really like these cumulative or these exceedance plots, where I basically take the absolute value of my modeled result minus my recorded value. I sort from smallest to largest, and I then assign a percentage value next to each target answer and just plot the data versus percentage occurrence. And in this graph here, each of those little markers, I guess, is a single peak flood mark, where everything less than a certain percentage should be a better fit than the one to the right. So that was 100 meter resolution, 50 meter. You can see we're trending down towards the x-axis, so it's increasing in accuracy. You've got that level difference on the left. So we're hoping to get down towards the x-axis. There's a 30 meter result. 20, 15, and 10 are in there as well. I wouldn't include these figures in a report, but for trying to see the sensitivity of these things, it's really useful. I'll just take you on a journey now through the catchment so you can see what sort of result we achieved. So you can see it's plus or minus 0.3 of a meter across the board. There's some outliers, but relative to the flood levels around them, I'm not worried about those. There's some outliers there in the middle. But I think they were probably potentially recording errors, but we left them in there anyway because it's important to see what sort of range there was. Nevertheless, it was a great calibration result. Really matched those recorded levels really well. The next example I'd like to show you is for the east coast of Australia in the lower Clarence Valley. It's a catchment which is around 10,000 square kilometres. To give you an idea of the flows out of this area in the 100-year event or 1% AEP, it's up around 19,000 cubic metres per second. There's been two really nicely calibrated models, or two studies done, which include great calibration of a TUFLOW model to this catchment. One done in 2004. I wasn't involved in that study, but the likes of, I think it was maybe even Bill, or maybe Greg Rogenkamp, Kathy Barton, they calibrated that model really nicely. Come 2013, Council received some new LiDAR data, and they're looking to update it, plus also calibrate to some more recent events. And that's the work that I did, was the 2013 study. If you want to see these calibration reports, the link is there. I highly recommend it. It's an excellent example of calibration. Let's now just look at the data that was calibrated to. So Council have 25 different, or the state as well, have 25 different water level gauge locations. So that's time versus water level. Since the 1970s, they've had 8 major flood events. These all represent the current topographic state of the catchment, so they're good for calibrating against, for flood model calibration. It's got that velocity recordings that I mentioned previously. The coloured lines there are the TUFLOW model result. The grey are recorded velocities, or it's actually flows, because velocity multiplied by the cross section will give you the flow for those historic events. And then loads of surveyed peak flood level data. So 600 surveyed peak flood levels across 3 different events from 2001. Let's use this model to test the influence of different, I guess, design assumptions on results. And I'll, just because of the size of the data set, look, I'm not going to show 25 different gauges and 600 flood marks. I'll just focus on that area in the pink. This here is our land use data set, all industry standard values we used. Here is the inflows and outflows. You know, you've got the Clarence River, 7 different tributaries, tidal boundary at the bottom, internal catchment rainfall. When we dropped in the LiDAR data and we tried to recalibrate to the 2001 event and the other 8, this is the sort of result we got. The recorded level is the blue dots, the model result is in red. That's 2001. There's our peak flood levels. We're about 2.5, 3 meters too high there. That's the 2000 event. It's actually exhibiting a similar trend to the 2001 event. That's something, you know, that's telling us something. And the order of the discrepancy is pretty similar, 2 to 3 meters. Horrible result. What could be the reason for that? First of all, I'll say, do not attempt to improve calibration by simply adjusting Manning's N outside your established industry values. Don't try and tune in your numbers by reducing your flows by using loss values that are outside those that are physically realistic. You need to be asking yourself, you know, what are the possible errors? And when I'm doing that, I'm always focusing on what I see as the most significant hydraulic features in a project area. So to start with, boom, bathymetry data. I noticed that was missing from the supplied data set. Let's drop that in. This is now how the calibration looks for 2001. That's how it looks for 2013. Looks pretty good. Let's now look at the peak flood level marks out in the floodplain, and all of a sudden it tells a slightly different picture. Here you see that the water levels in the floodplain are a little bit too high, in the order of, you know, 0.5 meter too high, and the levels in the river are a little bit too low. So that was 2001, this is now 2013. That histogram plot down there is in the bottom left is a really nice way to present this sort of data for a wide area. So once I saw those results, it was just a matter of adding in break lines to enforce those key hydraulic controls. So those ridges, levees, raised riverbeds, riverbanks. If you're using SGS, you don't need to represent those minor drainage gullies. But if you're not using an SGS scheme, they're also important. Here's the result after adding that input to the model. So you're getting a nice correlation now in the river, also in the floodplain. That was 2001, this is 2013. Also an excellent result across the board. What this really highlights to me is if you calibrate only using your river gauges, then you're potentially still not getting an accurate result out on the floodplain. You need those peak water level marks out in the floodplain to make sure the interaction between your river and your floodplain is accurately defined. It's a very significant feature hydraulically, and it's important that you get that right. All right, let's now talk about calibration reporting. We'll close off on this. You'll notice that I presented my results in a histogram format. I find these really intuitive, really easy to interpret, and something I'd like to see in most calibration reports, to be honest. I have noticed over the last decade that in addition to just the histogram, you're now seeing people also report, say, your mean, standard deviation, and also a measure of how many points are in that data set. A really nice real-world example of this is the Brisbane River catchment flood study, and a link there is shown where you can access that. It's just a great example of calibration reporting. So you'll often see the histogram plot, or alternatively, sometimes you'll see these plots where you'll be mapping or graphing the modeled result across the x-axis, and that's for water level, and your recorded water level across the y-axis. If you get a one-to-one relationship, you've got an exact match. If you don't, it can show trends where there's a mismatch. And you'll often see people reporting an R-squared measure of fit using this data set. For reporting, I find this one a little bit more difficult to interpret, or I find non-modelers do. During the model development and tuning in phase, I do find it useful because sometimes what you'll see is segments of your model where there's just a consistent offset. You might find for a 1 kilometre reach, the levels are all consistently too low. And this sort of mapping here presents that really nicely. So it's nice for tuning in those or identifying issue areas in your model like that. If you look at your water level gauge results, we're not just focusing on the peak here. We're interested equally in the peak value, the timing, the shape, so it's both the rising and the falling line. All those things are important because it means that you're getting the conveyance and the storage right in your model if you're matching all those things. I've noticed recently that people are measuring the goodness of fit of these data sets using a number of different coefficients or measures. You'll often see a peak ratio, a volume ratio, and a Nash-Sutcliffe goodness of fit. These reporting values I've just shown there come out of the Brisbane River study, which was subsequently, or I believe, sourced from the SEQ water metrics. That was just, that's not the golden rule. There are other opinions on this. And in researching this webinar, I came across a great blog written by Tony Ladson, and the link is down the bottom there. Just search up Tony Ladson and Nash-Sutcliffe, and you'll find that he gives quite a good description of different measures of fit. River centerline long sections. These were very common with 1D models. In a 2D sense, they can be a little bit misleading. So if you look at that graph on the left, that's plotted from the downstream end of the river reach on the right up to the upstream end. And you see there's a lot of scatter in the points, and the model result is sitting between there. So you'd say it's a good calibration, but it's hard to say how good it is. So on the left, you'd say it's an okay, reasonable calibration. On the right, if you actually look at those levels on each side of the riverbank, it's an excellent calibration. We're within plus or minus 0.1 of a metre. And it's just that physically there's super elevation around those bends meaning that, from one side of the river to the other, around a bend, you might see a 0.6, 0.8 meter difference in water level. It's due to that you're seeing that offset in those graft values, but it's actually an excellent calibration. Before we close out, I'd probably just like to talk about aerial imagery. I actually class this as actually a low quality calibration data set. There's a couple of reasons for this. The challenges with getting an image right at the peak, that's one thing. Secondly, more often than not, you'll find when people do comparisons against the aerial imagery, they do it from quite a zoomed out extent. And I can tell you from firsthand, it's pretty easy to make a poor result look good when you're looking at it from quite a zoomed out extent. In addition to that, often you'll see when you get these major flood events, the flooding will fill up the river, it'll then fill out the floodplain, and in major events actually go out to an area of the floodplain where there's higher relief topography gradients, and that's what that graph down the bottom shows as a cross section. And it means that, for a significant change in vertical relief, the horizontal, or the vertical level, the horizontal isn't all that much. What I do say though is it's still a useful calibration data set to support the others, because it might tell you, okay, my modeling, it shows that this area is dry, but it actually got wet. I need to investigate that a bit more. But I wouldn't use this as a primary source of calibration. It's more of a secondary or tertiary level of calibration. So, look, in summary, calibration is necessary. I want to see more of it, and this is very much speaking to the governments, cities, states out there that please, when there's an event, go out there and collect the data so that modelers have that data available when they're doing their work. Not only will it make those models more accurate, but there'll be huge cost savings in terms of flood damage and design costs. For the modeler, calibrate to multiple events, don't just model one. When you're going about doing that modeling, quality check all your data, just like I did mentioned in this presentation. Get a checklist, go through it, and be really systematic in your approach. Employ best practice modeling approaches, and also use a software that's suited to that type of hydraulic condition. And then when it comes to calibration reporting, it's really important that you document your results well, for the simple fact that that then becomes the reporting data set that people will use in the future to get a sense of the uncertainty associated with those model results. And if you lose that information, people can potentially use those models for situations where they're not well suited. I guarantee you on the chat line, someone has asked, well, what happens if I don't have calibration data? People have asked that every single webinar that I've been behind the scenes in the chat line. Well, I recommend you tune in on the 16th of June. That's when Bill will take the microphone and he'll be presenting on modeling when calibration data is scarce. That's that's it. Time now for question and answer.
What a feast. What a feast we've had. That's absolutely fantastic, Chris. And everybody, I'm sure, applauds the fact that you take such a measured approach to this. So thank you for that. And for Phil and Bill in the background, they're going like mad.
We're just trying to catch up.
I can imagine. I can see you been going, you must have, worn out fingertips.
Yeah.
Blasting away.
I'll go first if you want, Bill. I was just actually typing an answer to what are the considerations to select calibration events and what's the best approach to calibrate against water levels, steady or unsteady modes. And I guess the considerations in picking calibration events is the data that you can get your hold of, input data such as rainfall and that you're going to use to drive those boundaries, as well as output data to compare to recorded levels and flows and peak water levels across the catchment. Really important to have that data to be able to compare against. When picking calibration events, as Chris mentioned, it's really good to have a range of different event magnitudes. So if you calibrate your model only to in-bank events and then you use that calibrated model to calibrate to really large events where you've got a lot of the flow in the floodplain, you have less confidence in your calibration if you haven't done any calibration to those larger events. And the other one in consideration is often in how recent the event is. If we're looking at comparing back to events in the 1890s or something like that, it becomes much harder to get a good confidence in the elevation, taking your current land use conditions and rewinding that back to a much older event. And in terms of the comparator, whether or not we should be steady and unsteady, definitely if the data is available, unsteady models should be using, comparing the timing of your model peak and the recorded peaks is really important. That way you can be confident that you've got the routing right. You might get the peak water levels right, but if you're not comparing the timing, the timing may be well out because of your routing parameters. So yeah, that's my answer to that one.
So I was just typing an answer for the from Kelly G to how to manage calibration and adding breaklines within the channel, and it's not clearly defined. Example, several braided streams. I think that probably in all my years and many model calibrations, the thing that has been most important is actually your terrain, your topography, your bathymetry. If you don't get the terrain right, you don't get your bathymetry right, you're always going to find it hard to get a good calibration. And Chris demonstrated that a bit through the Clarence model there by, if the levees are missing, you're not going to get a good calibration. So it's just, yeah. So I think in answer to that question, you really need to go and source some high quality data if you don't have a good definition of the channel. And when you're doing this, the most important thing is to think about where most of the water is flowing. Not necessarily the backwater areas, but where the water is moving, because that's the most influential part of the system. And that's what's going to affect your model calibration the most.
Where would you like to head next? That's how to manage.
I can take Lucas's one. Lucas just asked, how do we create different histograms in QGIS? Actually, don't use QGIS to create that histogram. What I did is I got the maximum water level raster from my my simulation. I did a point inspection of that with my recorded data set, just subtract one from the other, and then bring that into Excel. And if you go to the data analysis toolkit in Excel, you have to click on the add-ins. You can add in histogram via that feature there.
In fast developing catchments, how is calibration used on historical events in improving the accuracy of the model?
Still not sure what you mean by fast developing catchment.
I think what you're saying is the catchment state is changing. So if you're in an area where there's lots of development, basically what you need to make sure of there, Mehdi, is that the catchment state at the time of your event is represented in your model. So I typically build my model for the current state, and then you backdate the features to match the condition at that time. So if there was a highway that was built that traversed the floodplain, I'd use the Z-shape option in TUFLOW just to cut that out. And that way, that major hydraulic control is subsequently removed from the model to represent how it was when that historic event occurred.
Yeah, it's not really relevant to the presentation, but could you please tell us about the key differences between with HEC-RAS? Look, I mean, whatever we say will probably be seen as biased, but certainly what we're seeing, there can be some pretty substantial differences, and particularly where the flows get very complex. But I won't elaborate on those. But and I think model calibration really, basically a solution scheme is fit for purpose if you can calibrate using industry standard parameters. If you have to start using false or excessively high or excessively low Manning's end values or ridiculous bend losses, that means that either your data that you're fitting in is not good or your solution scheme is not appropriate for that problem, or both those things. So I just want to reinforce what Chris was saying about as soon as you start going outside the bounds of industry standard parameters, there's something else that is wrong. So, yeah.
Moving on to Usman's question, I'm just picking the top three, and thanks everyone for prioritising questions. Hit that prioritising button, everyone, if you want the questions to come up higher in the priority. So Usman, what should be the model spinning period? What does it mean?
So by spinning period, I'm guessing that Usman's referring to like a warm-up period where you let the model reach like a state, and that's probably relevant for tidal and estuarine models, for some flood models higher up, there probably is really not much need for that. Is it a warm-up period for the modelling? But certainly when you talking about salinity calibration and things like that, there may well be a requirement for a warm-up period in order to get that right. In terms of getting the velocities and things like that, if you warm up for a single tidal cycle, I think you probably should be getting a pretty good velocity field within the model. If you're unsure, I guess you can always run a bit of a sensitivity on that. How much difference does it make to your model results if you warm it up for a longer period or a shorter period? And if it's not making a difference, then you could probably get away with a shorter period.
Yeah, I can say that the results should inform that answer. You know, if you model for a neap and a spring tide cycle and you find that that model result starts lining up with the real world result, and thereafter the calibration looks great, well, you know, that's informed how much time you should be using to spin up the model and warm up for those salinity simulations.
Okay, what about Gary's question at the top there? In what context or situation do you think it's more important or relevant to talk about precision rather than accuracy?
Yeah, I'm not sure, Gary, if you mean by precision, you mean numerical precision, as in, which can come in different forms. There's obviously the mathematical single double precision that's used by processors. That's not really an issue in flood modeling for schemes, except in some situations. But accuracy or understanding your uncertainties or your inaccuracies is the most important thing. You know, your uncertainties, often most of your uncertainty might come from your rainfall data, because you just might have one pluvia or one gauge outside the catchment, and really don't have a good handle on how much rain actually fell on the catchment. So you really just need to understand where all your uncertainties lie, and then that will help you evaluate, you know, the level or degree of accuracy you would be seeking in your calibration. So if you've got very, very high uncertainties, don't expect a great calibration across a range of events. But if you've got great data feeding in, you've got lots of rainfall gauges, you've got great bathymetry, you've got stream gauges. You know, a great example is the Brisbane River study. It just was flowing with volumes of data. And the end result is you end up with a really good test and a great calibration model that can cover a wide range of events. So it's just about understanding your uncertainty. And from a consultant through to the client, it's just about all parties understanding that inaccuracy and working from that base.
Why don't we just do two more and then call it a day, shall we? There's two up the top there, one from an anonymous and another one from Jeffrey Newman.
Oh yeah, it's probably a good point. Yeah.
So can you read out the question first?
Yeah, sorry. Yeah, it's independent calibration and validation data sets. This was a must when I was at uni for hydrological models, but I do not see independent validation as much for 2D, 3D hydraulic models. Yeah, and actually I'm a big fan of having the process where you might calibrate to 2 or 3 events, and then you don't necessarily run those validation events until you finish a calibration process. You know, I think there is some merit in taking that approach, but you do need quite a range of events. I think the reason you might not see it so much for hydraulic models is just the lack of data. You know, a lot of hydrology models, there's stream gauges, which is often a long historical record that they can work to. But for hydraulic models, it's just often there's unfortunately a real lack of or shortage of data, and often from very recent flood events, which is, of course, to be honest, completely unacceptable. You know, as soon as there's a good flood event, there should be a wealth of data collected from that event.
I feel like one of the issues with having such lovely looking 2D model results is that some people don't think that data collection is necessary anymore, because the model will just tell you the answer. Couldn't be further from the truth. You still need that data to calibrate, validate, you know, get the right model result.
Why don't we call it a day? Are you happy with that, guys? Or you got another burning question you want to rip out of those list of questions? Thanks everybody for your questions.
Yeah, we'll work through all the questions, Trevor, after the today, and
thanks for that.
And put up answers, and you, I believe you'll host those once we send those through. Yeah,
absolutely. Yep. No, that's been great. Thanks everybody for joining us today, and particularly, when you've been listening to people with not only the theoretical knowledge but also the practical knowledge, go out there and measure and make sure the line you're seeing isn't the seepage up the door. It's actually the height of the flood. Yeah, that's excellent. Excellent work, practical and theoretical. 3 areas: on-demand courses, webinars with TUFLOW, and the live training online. You can see on our website. You can get the details on the website, but there's just a host of stuff going on there. I think we've done it all. Is there anything I've missed? I'm reading all the notes that people are sending me, and I think we're right. I don't think I've left anything out. Thank you so much, Chris, Bill, and Philip. It's been an absolute, as I said, a feast of information and deep knowledge, really good deep knowledge. Appreciate it so much. And as I said, a measured, systematic approach to this has been wonderful. Thanks so much for your time and effort, and for everyone joining us. So bye for now.
Yeah. Thanks, Trevor. Thanks all.
Trevor.
Yeah, thanks, Trevor. Thanks, everyone.
Great news. Been great. Thank you.
Thanks for watching. Subscribe by clicking the link below and click on the notification bell to stay up to date with new releases. For the latest in significant, innovative and critical advances in water science, technology and management, subscribe now. To build your skills, enhance your technical knowledge and learn from leading experts in water, visit theaustralianwaterschool.com.au and discover our online training courses, both live and on demand.